Okay, we're shifting gears now, and we're going to talk about causality, which really we're talking about why is it that variables are related? What are the different reasons that can make variables related? So cause, as I'm going to use it, means to affect, influence, result in, lead to, or affect the likelihood of. Now, two variables can be, this is really the key point here, and I know that many of you see this and know this, but the key point is that two variables can be related even though neither variable causes the other. So, for instance, here's an example. Which type of music, rock or classical, do you like? And how much do your bones ache when you wake up in the morning? Well, we introduced confounding variables in Chapter 1. And so a confounding variable, is the variable that brings about a relationship between two others. So this relationship between type of music liked and bones aching is not causal. In the relationship that we'd see here is, people who listened to classical music would tend to have greater aches and pains in waking up in the morning. And the reason that would be so is that people who prefer classical music tend to be older than do those who prefer rock. And it's the fact of being older that's leading to the greater aches and pains, not the classical music. So here we've got the confounding variable age bringing about this relationship between preferred music and aching bones in the morning. So this word causality is in essence conveying, well, can we figure out what causes what? Have we got a causal relationship? Or on the other hand, have we got a relationship that's been brought about by a confounding variable? And sometimes the research design lets us figure out the question of causality, and in other times we're left wondering whether the relationship is or is not causal. So, here's a definition of a causal relationship, and that is that one variable in the relationship actually affects the other. I'll just mention it's possible that each variable could affect the other variable, but if at least one affects the other, we've got a causal relationship. On the other hand, relationships can occur due to confounding variables. And I sometimes use the term third variables. So confounding variables are variables that affect the pattern of association between two other variables. And so by pattern of association, I'm meaning that confounding variables can affect size of association, presence versus absence of association, or direction of association. By direction of association, I'm meaning is the relationship a positive or a negative one. And again, in our example, the confounding variable age, it was the explanation for the association between type of music and amount of aches and pains. So this chart here is going to sort of show you a very simple example of a confounding variable. It's not the best example, but it will work for our purposes. So let's go look at the bottom row in our table. And so the notion is here we've got 100 kids in foster family placement. We've got 100 kids in group home placement. 24% of the kids in foster family placement versus 36% of the kids in group home placement have behavior problems. We've got a difference in percentages. I mean, as a matter of fact, that difference is a difference of 12 percentage points, but the difference in percentages conveys relationship. So what we want to do next is see if we can get some handle on why we have this relationship. Is this relationship a causal one? In other words, I mean, is there something about type of placement that affects whether kids have behavior problems? I mean, we're seeing lower percentages of kids with behavior problems in foster family. Can we conclude that there's something about foster family versus group home that leads to reduced behavior problems? So it's almost the logic is a reverse logic. What we're going to try and do is see if we can identify a confounding variable that's bringing about the association. And basically, if we can identify a confounding variable that's bringing about the association, then the relationship is not a causal one. So one way to control for a confounding variable is using a table. So basically what we do is we create subgroups within our confounding variable, and then we look to see within a subgroup, do we indeed have a relationship? We have two subgroups here, and so our confounding variable, or we can say our potential confounding variable, is age. So let's look at kids who are 10 and younger in foster family and group placements. And you can see that in this age group, in the subgroup, we no longer have association between behavior problems and type of placement. We've got 20% in each placement type with behavior problems. Our difference in percentages is 0. So in the younger age group, the relationship that we saw for the full sample no longer exists. And then let's look at our kids 11 and older. Here, I mean, we have higher percentages with behavior problems, 40% versus 20% in both foster and group home settings. But our key comparison is the percentages in the foster versus the percentages in the group for our 11-year-olds, and those percentages are 40% in both placement types. So we have an absence of association also in this older age group. So in sum, what's happened is that when we control for age, the relationship disappears. In other words, we don't have relationship within our subgroups. So, I mean, you know, this slide summarizes the data from the prior one, and the basic conclusion is that within the age groups the relationship has disappeared. So what we reason is that the relationship between type of placement and behavior problems was due to the confounding variable of age. So in essence, in this situation, the relationship that we were seeing was not a causal one. In other words, in this situation, type of placement was not affecting behavior problems. We got our relationship between type of placement and behavior problems due to the confounding variable age. You know, and just flipping back here, I mean, why did we see a lower percentage of kids with behavior problems overall in the foster family placement group? In other words, why are we getting 24% here and 36% here? Well, it's because most of the kids who are in foster family placement are young. 80 of the 100 kids are 10 or younger. So that is the group that has lower levels of behavior problems. That's the group in which only 20% have behavior problems. On the other hand, look at the group home placement here. Most of the kids are in the older age group, and kids in the older age group are more likely, 40% versus 20%, to have behavior problems. So it's an association of age group with type of placement that's bringing about the relationship that we see. We've got fewer behavior problems in the foster family settings, not because foster family placement brings about better behavior, but rather because the kids in foster family placement, much more often than those in group home placement, are younger, and younger kids are less likely to have behavior problems. The next chapter is going to expand on confounding variables and how they affect relationships. So the purpose of this table and discussion here is to give you the big picture. So I want to acquaint you with the two most basic quantitative research designs: the experiment and the survey. In the experiment, the researcher manipulates the environment. And the manipulation that the researcher invokes, or the key manipulation, is termed the intervention, or the treatment stimulus. And the intervention is what is done to the participant. So for instance, an intervention might be a cognitive behavioral one to help a kid stay in his seat at school. In contrast to experiment, in the survey there is no manipulation and there is no intervention, at least in the same sense as in an experiment, but rather what happens in a survey is that the researcher simply takes measurements. In the experiment, the researcher manipulates the environment and introduces an intervention and takes measurements. In the survey, the researcher simply takes measurements. So, key idea that you've got to take with you is the notion that experiments are greatly preferred to surveys for drawing causal conclusions. Surveys are about describing data. Very often in a survey, you'll find relationships, and you won't logically be able to tell whether those relationships are causal or not. In essence, the relationship may be causal or it might not be causal. The integrity of the survey design isn't usually sufficient for letting you draw a conclusion about the cause of a relationship. You can describe data, you can find relationship. Conclusions about causality are going to be limited. On the other hand, experiments are all about causality. Experiments are designed specifically to assess the effect of the intervention on the dependent variable. And just as a general rule, experiments are far preferred to surveys for drawing conclusions about causality. There are different types of experimental research designs. Some are better than others. Some are better for drawing conclusions about causality. But as a group, your experimental designs are far preferred to your survey designs when the purpose of your work is to determine causal relationships and to draw causal conclusions. Now, there are many, many different types of experiments, and we're not going to go into the subtypes and the subtypes of experiments. But I just do want to mention that in the straightforward, basic way, by far the best experimental design for drawing causal conclusions is the true experiment. Now, the term true experiment's disappearing just a little bit now. So alternative names for true experiment are the randomized study, the randomized trial, or the randomized clinical trial. Now, a true experiment is distinguished by one particular characteristic of its research design. True experiment is then therefore defined as a research design that uses random assignment to groups. Here is a definition of random assignment: the use of methods of chance to assign cases to groups. In an experimental situation, your groups, in essence, receive different interventions. So group 1 might receive the cognitive intervention, group 2 the talking therapy intervention, group 3 might be a control group that receives no intervention at all. But your groups, in essence, each receive a different intervention. Now, random assignment to groups, pragmatically speaking, eliminates confounding variables. So, this is the big kahuna, as the expression goes. Confounding variables can create relationships between other variables, even though neither of the other variables affects the other. So confounding variables bring about relationships. So therefore, in non-randomized designs, in designs that don't use randomization, you see relationship, and it's almost without exception very difficult to know whether that relationship is due to the causal effects of your intervention or to confounding variables. So in the true experiment, which is to say, in the study that uses random assignment, there are no confounding variables. So this helps the drawing of causal conclusions immensely. I don't think it's oversimplifying to say that in true experiment we can know the reasons for the relationships that we see. We can draw causal conclusions in true experiments due to the randomization process. Another way to think about the random assignment is that random assignment is eliminating factors that bias comparisons between groups. Now, factors that bias comparisons between groups are really the same thing as confounding variables. And, in a pragmatic sense, random assignment is creating equivalent groups. That is to say, as the study begins, the groups are very, very similar. So, Chapter 1 presented a brief example on randomization. So the example there is that a statistics professor assigned students to a computer teaching module or to a teaching assistant, and then the dependent variable is score on the final exam. Now, so there are several ways that the students could be assigned to groups. Suppose that the professor randomly assigns students to groups, which is to say, perhaps the professor put all of the students' names in a hat and randomly drew, in other words, used a method of chance to assign. Randomly drew names to determine who went to the teaching assistant and who went to the computerized teaching module. If the professor has used random assignment, the professor can then therefore be sure that differences in outcome, in other words, differences in mean final exam scores in the two groups, that those differences aren't due to systematic bias, which is to say, to confounding variables. With random assignment, the assignment to groups is simply based on luck. It's the luck of the draw, and in studies that use random assignment, the professor can be confident about causality. So basically, if the professor sees a substantial difference in performance between the two groups, the professor knows that that difference is due to the intervention. So if the professor sees the students doing, in the computer module, doing better than those with the TA, the professor can confidently conclude that that difference is due to the superiority of the computerized module in comparison to the TA. Now, suppose that students choose their own groups, or for that matter, suppose that the professor assigned students to groups based on her perception of student needs. So this is an example of a study that does not use random assignment. The process of determining assignment to groups has not been carried out by a method of chance. So when you have non-random assignment, factors other than luck can differentiate the groups. So another way to say this is that when you have non-random assignment, there may be confounding variables involved. So now let's picture, again, the notion of the students choosing their own groups. And let's again say that those who do better are in the computerized teaching module. Why did students in the computerized teaching module do better than did those with the TA? Well, it may be because of the intervention, but because the assignment process is non-random, there may be confounding, which is to say biasing variables involved. So for instance, perhaps the students who chose the computer application are, as a group, better in math than are those who chose to work with the TA. Consider perhaps that learning the computer module involved considerable upfront time. Well, if that's the case, perhaps those who chose the computer module were, as a group, more motivated than were those who went with the TA. Or perhaps those in the computer group had lower levels of math anxiety. Perhaps that's why they had the confidence to go ahead and work on their own with the computer program rather than with the support of the TA. So in short, given the absence of random assignment, there's no way to know, there's no way to logically unravel whether the better performance in the module group is due to the greater effectiveness of that intervention or due to one of the confounding variables that I've mentioned. And indeed, perhaps I'm not thinking of another confounding variable. I mean, it might be the case that the students who are in the computerized module had more intensive coursework prior to the beginning of the course, and that could be still another factor entering in. So, in short, in the absence of random assignment, it is very difficult to draw a causal conclusion. It's very difficult to know whether a result or relationship that you see is a causal one rather than one that has occurred due to confounding variables. And so this is the great advantage of randomization, is that you don't have to worry about the bias that comes from confounding variables because, in essence, there are none. Now, we do need to mention a caveat here. Random assignment does not create precisely identical and equal groups. Even with random assignment, groups may and almost always do differ simply due to the luck of the draw. So in other words, random influences are not eliminated. By chance, one group might have a bit more math ability, for instance, than another, just because by luck of the draw, those with better math ability tended more often to end up in one group rather than the other. Random assignment doesn't eliminate random differences, but it does eliminate differences due to confounding variables. There's no systematic bias. There's no bias in the sense that those who are more motivated, because they're more motivated, choose a particular intervention. The differences that exist are random. So I've given you a pragmatic message, which is to say that random assignment eliminates confounding variables and allows the drawing of causal conclusions. That's the key message. Keep in your mind that random assignment doesn't create identical groups, that there still are random differences. And we're going to discuss random differences, you see, when we get to statistical significance tests. That sometimes you can get relationships just due to the luck of the draw, and your statistical significance test can help you decide whether the relationship is a big enough relationship, in essence, so that it's not likely to be due to luck. Now we're working much more on research design, which is to say, can we rule out the systematic bias that confounding variables bring about? And we can do so in designs with random assignment. And I am going to just very quickly mention two other types of experiments. I've mentioned the true experiment and really emphasized that. These are terms that perhaps are good ones to know as you move forward to your research methods course. Quasi-experiment. To give a rough definition, quasi-experiments very often have two groups, but assignment to groups is non-random. Quasi-experiments very often have some limited ability for the researcher to be able to draw causal conclusions. But the degree of certainty or confidence that the researcher can have in the conclusions that she draws, this confidence is much less the case than is so in a true experiment. Some experiments are carried out with only a single group. And without getting into too much time on this, it is very difficult usually to draw conclusions about causality when there is only a single group. Oftentimes the ability to know whether relationships are causal in pre-experiments is hardly, if at all, better than in a survey. When we get to chapter 22, we'll talk about single case designs, and you'll see that the situation is a little bit better there than is so in pre-experiments. So that wraps up chapter 10, and the big idea is that random assignment eliminates confounding variables and basically lets researchers draw conclusions about causality, that is, about what causes what.